folks, and welcome to this lesson on stereoisomers and alkenes and cyclic compounds. By the end of this lesson, you should be able to define and identify stereoisomers and name and draw cis-trans isomers of alkenes and cyclic hydrocarbons. So first off, what are stereoisomers? Well, you do have your many different types of isomers, and stereoisomers are one of those types. Specifically, they're the type where they have the same connections. Everything is connected in the same way. So you have this in any particular carbon, what is attached to that carbon is the same and all of that, but the arrangement is different. There are two ways that you can get stereoisomers, and one of them is when you have rigidities in bonds. So most of your sigma bonds, most of your single bonds are able to spin, but there are a few types of bonds that won't spin. And so when you have that type of a bond, this is one way that you can have all the same connections, but having the arrangements be different. The other type is when you have a lot of different things attached to a single carbon. Now the thing is that if you draw the second type on a piece of paper and you're just using like the 90 degrees and all of that, you're not going to really see the stereoisomer part of that for those ones. But if you look at these molecules in three-dimensional space, you will see that they are actually different. For this lesson though, we are going to be working on, or we're going to be talking about this first type, that type that you get when you have that rigidity in those bonds. So first things first, let's talk about the whole bond rigidity thing. So let's say we have this particular hydrocarbon. You can see that it has only single bonds, and you can see that basically what I'm able to do with this model is I can spin around any one of these single bonds. So you can see that I'm taking the same model, and yet I'm able to make a whole bunch of different shapes with it, but I'm not actually breaking any bonds, I'm not making any new bonds, I'm basically just taking the same thing and just moving things around, literally just spinning things around on what is already there. That's what happens when you only have single bonds. That's what happens when you only have those sigma bonds in there. However, when you have double bonds, what happens is that because of the pi bonds and their directionality and the fact that you have these electrons that are going to repel each other and so on and so forth, you can't actually spin the carbons around a double bond. So this structure that I have made, this is going to be the way that it is. The only way that I can go from, say, this to this is I would literally need to break the bonds so that I take things off and then put them back on again to arrange them. So because of this, what I had before, so this particular configuration ends up being something different compared to this one. So these two, even though I have the same number of carbons, I have the same number of hydrogens, and I have the same number of what else is on there, because of the fact that I can't twist this, these are literally different things. I would have to literally react things, break bonds, then make them again to make them the same molecule. So these two are distinct from each other. So if we do have particles that are different from each other, we are going to need a way to name them differently as well. Depending on the type or what connections you do have, the naming system that you're going to use is going to be a little bit different as well. The first naming system that we're going to look at is the cis-trans naming system. So what you need to be able to use that cis-trans naming system is you have the two carbons around that rigid bond, and each carbon has to have one hydrogen. Now, why is that? Well, if one of the carbons had two hydrogens on it, then basically I can take this entire structure and literally just flip it vertically and you would end up getting the same thing anyway. There's no isomer in this particular case. These two things are not distinct. You literally just took one and just flipped it around. And you didn't have to break any bonds for that. They just literally are the same. So you can't have two hydrogens or two of the same thing on one of the carbons. Now, if you had a case where one of the carbons or both of the carbons didn't have any hydrogens at all, well, you can still get a stereoisomer. This is not going to become this unless you break bonds and make them again. Again, this is not a case of you can flip it and therefore it's the same thing. But in this particular case, where your carbons don't each have one hydrogen, you would actually use a different naming system altogether. And so that's why when you're using cis and trans, you have to have one hydrogen on each carbon. So here we have two diagrams of but2-ene, but as you can see, they look different from each other. And so, of course, we need a way to distinguish them using their names. Whenever you're using your cis-trans naming system, what you're going to do is draw an invisible, or visible if you're working through the problem, line across where that double bond is. So you're drawing the line where the double bond is. You have a carbon at each end, and then you're going to have your other stuff. For cis-trans, what you're going to do is figure out where your hydrogens are. If your hydrogens are on the same side of the dotted line, like this case, this is the cis stereoisomer. And here you can see you have your hydrogens on each of your carbons. You can see that they are on opposite sides of this line. And so this one is trans but2-ene. Now, something that might help you remember how this works is that you have actually probably seen by this point the prefixes of cis and trans before in real life. Usually you're going to be talking about gender in that context. So you've probably heard about cisgender and transgender. Cis means same. And so in the context of stereoisomers, your hydrogens are on the same side of that double bond. Whereas trans means different. So your hydrogens are on different sides of that double bond. And so yeah, with cisgender, your gender matches up with what you were assigned at birth, and as opposed to transgender, where your gender is different from the gender you were assigned at birth. To be a little bit embarrassing, my high school teacher taught me a little dance to remember how these all worked. So I take my shoulders as that double bond, and then you have cis, cis, trans, cis, cis, trans. So yeah, you can also do a little bit of a dance to remember which one is which. Now, I've also mentioned that you can have this kind of stereoisomerism with cyclic hydrocarbons as well. So here is my cyclohexane. As you can see, you can still have a little bit of wiggling that can happen. So there is a little bit of shifting that can happen, but take a look at this. Let's focus on these two carbons. You can see that I have two things attached to each one. Whites are our hydrogens. So you can see that when we look at where the circle is, so that's this carbon-carbon bond, it goes around to make that cyclic ring. You can see that both of the hydrogens in this case are above the ring. Now, I did say that there is some shifting that can happen within the ring itself, but look, no matter what I do, where those hydrogens are relative to where the ring is isn't changing. They're always staying above that ring. I can't actually change it so that one of these is on the other side unless I break this bond, turn things around, and then reconnect them again. So here we have two 1,2-dimethyl cyclopropanes, but as you can see in this particular case, here we have our line where our ring is, and then Here, I've highlighted those hydrogens. So each one of these carbons does have one hydrogen each. So in this particular case, when you're taking that ring and you're using it as this sort of splitting line, both these hydrogens are on the same side. So you have cis, 1,2-dimethylcyclopropane in this case, and in this case, you have trans, 1,2-dimethylcyclopropane. It works in the same way. You can't actually change any of these side chains without actually breaking bonds. So use that rigid bond, or where that bond rigidity happens, as your sort of determining point. See where the hydrogens are. As mentioned, there is another system that you can use when you have your carbons don't each have their own hydrogen. So this is a case of that. This carbon does have a hydrogen, but this doesn't. But you can see that you have these two particular particles, which are sort of mirror images as well. Now, in the case where you don't have hydrogens on each of your carbons, you're going to have a different naming system. You use E for what used to be trans. So you look at your biggest groups, so to say, and then you take a look at where they are compared to each other across that line. And so here we draw the line there. Your biggest groups are opposite each other on that line. So you use E and then the rest of the name. So E is basically what trans is in the other system. And then Z is when you have both of them being on the same side, and so it's the equivalent of the cis. The rules that you use to determine what the biggest groups are based on the Kohn-Ingold-Prelog rules, which I'm not going to go into because I'm not going to make you name any EZ stereoisomers. Annoyingly, sometimes drawing these cis stereoisomers can be more challenging. So, if you know that you have an alkene and it is a cis one, draw the double bond first. After that, figure out where you want your hydrogens to go. So I'm going to have my hydrogens going that way. So my other stuff is going to go this way. And then start drawing everything else in. I know this is going to be but-1-ene, so that's going to be carbon 1 and 2. On my carbon 1, my other thing that is on here is chlorine, and then there's nothing else, so that means we have 1, 2, 3, and then 4 carbons. And that will get you that drawing. You can see that instead of doing the nice up and down shape, you have a little bit of a kink that happens, and so this is why I suggest draw that double bond first, and then draw the rest of it. Another bit of a weird naming thing that can happen is that if you have more than one double bond, then you actually have to toss in this A back into the name. So typically, if this were just a pentene, so you only had one double bond, there would be no A. You take out the A and the E is what replaces the A. But for some strange reason, if you have more than one, you toss it back in. I don't know. At any rate, that's the end of this lesson. I'll see you next time.